plotted the different orbital elements. So here you have the semi-major axis I could find in databases. Here you have the eccentricity, and here you have the different inclinations. So obviously it's way too wide, and there's probably a lot of meteors there that are not really Taurids. Obviously we have some very, very high eccentricity that makes no sense, and even the this also don't work. So I was like, okay, let's just focus on the highest concentration here, which is there we go. So this is just a zoom basically in the middle here, which is a bit better, but we still have a lot, very wide inclination, and same for every other orbital elements. So in the end, I decided not to use this, and I just went to take a look at the theoretical data that's given in the Meteor data center that we heard a lot about today. So they give the data from the Taurids, and I decided to use those simply and to create initial conditions from there. So what I did was simply to integrate those particles for 1,000 years and to compute the chaos as we go along. So I decided to choose the radius of the particles so we could neglect the non-gravitational forces in order to focus only on the gravitational aspects for now. So these are the maps I obtained. So the way they work is very simple. So here you have the initial semi-major axis of the Taurids, the Northern Taurids and the Southern Taurids. Here you have the initial eccentricity for the particles. And in color, you have the chaoticity. So the darker it is, the more stable it is, and the lighter it is, the more chaotic it is. The scale actually is cut. So I had particles that were even more chaotic, which shows that these are very, very chaotic streams compared to the previous one I've studied. Another thing we can notice is if we compare the Northern and Southern Taurids, so of course their orbital elements are slightly different, but if we compare this part here and this part here, which is the one they have in common, we can see that the maps look really similar. And in order to focus my work on one of them, I decided to focus on the Taurids, on the Northern Taurids, because yes, they look similar enough and it was just simpler. So what can we say about the maps of the Northern Taurids? Well, we can see very well there's one area here, one there, and a small one here, and they are all much more stable than all the others one. I don't know if you can see very well on this map, but yeah, it's clear. So why are those areas much more stable? What I've seen in previous maps is that usually when that happens is because we have mean motion resonances with a planet. So very quickly, if you don't remember what mean motion resonances are, it's very simple. You have two bodies and their orbits are proportional to one another. And in some cases, and this is the case in these schematics here, you can see that the two bodies never encounter one another. So here you can see very well this body and this one will never meet one another, which means that we have a much more stable orbit for the small blue particle here. So this is how we obtain those large dark areas on the map. And I wanted to see if that was a reason for the Northern Taurids dark areas. So I checked a lot of planets and it worked very well with the Jupiter. So with Jupiter, we have these two lines here that fit very well with the dark areas on the left. So I thought this is probably what's happening. But we have the third dark area that do not fit with any mean motion resonance with Jupiter, but they also don't fit with any other mean motion resonance with any other planet that I could find. So, okay, why do we have this third stable area? So, to find that out, I wanted to go a bit deeper in the effect of Jupiter on these Taurids, on the Northern Taurids. So, I redid the exact same integration, but I took Jupiter out of my integration, and this is the map I've obtained. So obviously the first two dark areas have disappeared, no mean motion resonance with the planet that doesn't exist, but we can see that the third dark area also has disappeared, so it's much more chaotic now, which means that Jupiter is definitely responsible for the stability, but the mechanism for it is not a mean motion resonance, but something else. And I don't know what is the something else. So now the rest of my work will be to focus on finding out what mechanism Jupiter can use to stabilize this part of the Taurids. But yes, very quickly, a small conclusion on the Taurids. So first, you saw I had some troubles using orbital elements from the data I found. Then we saw that the Taurids is much more chaotic than the other streams. And I think the reason why we have so much trouble with 2p Enki and the link with the parent body is definitely linked with this. Next steps on my work, I want to verify the mean motion resonances I found, and I also want to keep working on this mechanism that would stabilize the third area. If any of you have ideas or want to discuss this, I would be very happy. And in the future, I also want to have the non-gravitational forces, of course, to see how it would modify the maps. That's it. Thank you for listening.
So I see no questions online. No, I don't know if there is any question. Okay, there are questions here, so please, Lubos.
Just a comment. Orbit of parent body, comet NK, is subject of quasi-Io resonance, very strong. The orbits turn relatively fast. And in connection with selection effect that note Southern Taurids as well as Northern Taurids cross the Earth orbit periodically, but in other place. So there are gaps, there are expected gaps in Northern and Southern Taurids. It's nice. This evolution of orbit can be seen well in a picture we published with colleague Tomko a few years ago. I don't remember if in monthly notices or astronomy and astrophysics, but in this picture is nicely seen how the orbit liberates and this effect of the quasi-Io resonance. Thank you.
Okay, thank you.
Okay, we have for just one last brief question, please.
Hi, Ariane. Thank you for your talk. I was wondering, when you're doing your simulations and you remove Jupiter, how do you keep, do the other planets still orbit in the same way, or how do you keep ensure that you're just isolating that one effect, just on the particles?
Yeah, that's a very good question. So what I have is simply in my code, I simply look up the ephemeridus of each planet. So when I take off Jupiter, I just stop looking at the ephemeridus of Jupiter and just go from Mars to Saturn. So technically, the effect of Jupiter still exists in an indirect way because the other planets have the ephemeridus are computed taking into account Jupiter. But still, we see the direct effect on the maps, so that's enough for what I wanted to do.
Okay, so we thank again to all the speakers. The session is now over.